right? And then we'll go on. So let me share the screen to this one. Right. So last week, where we reviewed oscillators, and we spoke specifically about the Weinberg oscillator as one typical example of them. And then we spoke about regulated power supplies, and we went through the power supplies lectures, ending with the short circuit protection and so on. We had a discussion here. The main difference between this and everything that we had before had to do with the fact that we're using a Darlington transistor, which is essentially a double transistor in this circuit, to in this circuit instead of a single pass transistor. Okay, so all things are possible, but the analysis is always the same. One, you remember the operation, how an op-amp works, what does it do, the virtual earth behavior, so that allows you to kind of calculate voltages, for instance, at the inputs of the two inputs for the op-amp. And then from there, everything else is largely is normal circuit analysis, currents, voltage, resistances, and so on. Right? Today, now, question 3 has to do with negative feedback amplifiers, and there are a number of questions. Forget part C because we didn't do the design part of it. But as we can look at it on just as a circuit theory exercise, without knowing anything about what the circuit actually does, just to show you that even with this, that you know enough to analyze the circuit from what you have done before. But it is not part of our syllabus, and it's not going to what do you call it, figure in any exam going forward, right? So we have a couple of questions here, things we're talking about: gain stability, negative feedback amplifier, open loop gain, and so on. So that will motivate our discussion today, and the revision topic is feedback amplifiers. All right, so let me stop that and get to the actual slides themselves. All right, so to share feedback amplifiers, right? Okay, so this would have been one of the last topics that we discussed in ECNG 2012 as well. Okay, so some of this builds on what we did before. Some of this builds on some things that we have discussed even in the signals course as well. And the emphasis here is on understanding what is going on rather than the actual electronics design. There are some circuit examples in here, but we didn't spend time on that because I was more focusing on people understanding what we are trying to do. And if you understand what we're trying to do, then I could sort of apply it to these circuits afterwards. All right, so our discussion is on what exactly is feedback amplifiers, why we have to have it, and what types of feedback exists. Right, so remember, okay, this is a general block diagram configuration. Remember, most times when we design a circuit, we have an amplifier in this that we've designed, right? It could be op-amps, it could be transistors, and so on. The thing about it is that amplifiers by themselves are susceptible to some issues. Among the issues that you want to have working well with the amplifier are these things. First off, you want an increase in input impedance. If you think of an amplifier as being part of just a simple network, right? So you have an amplifier here, right? Whatever else the amplifier is, if you attach it to a source, right? Remember our source, and I'll just put a voltage here, right? Remember our source has, like a voltage source has a voltage, and of course all sources have a resistance in them. When you put that to a circuit, wherever the circuit is, and in our case we're dealing with specifically with amplifiers, what you want anytime you have a situation like this, where a source is connected to the input of some other circuit, what you want is that the input impedance of the circuit must be much higher than the source resistance or the source impedance, because simple voltage divider theory will tell you that if RA is much bigger than RS, the majority of the signal is going to appear here. If you don't have it that way, then what happens is that the majority of the signal is going to be dropped across the source resistance, which is inside of the source. And what you're going to get useful is going to be a lot smaller. Remember, this the signal at your amplifier input is what you want. So you want to maximize that. So the goal of most amplifier designs is to have a high input impedance, right? We'll look at why feedback causes that in a second. Is to have a high input impedance. The other thing is that the amplifiers are supplying a load, and the reverse now goes. When you put something on the output of the amplifier, you remember the amplifier has a output impedance. So when you send the signal out, you want the majority of the signal to be dropped across the load, not wasted inside of the amplifier. So on the output side of the amplifier, you want low output impedance. So generally for an amplifier, you want high input impedance and low output impedance. And that, if you remember from a circuit theory, that is when you get something called maximum power transfer. Right? When the output impedance is lower than the input impedance, the output of the device, you get the maximum power transfer because the majority of the voltage is being dropped across the output. The other thing is that all electronic circuits, you have semiconductor devices in them. They get warm, they get old, you get some variations, and you buy, remember these things are made in bulk, they're made by the millions. So you buy one and you are assuming that the specifications that you get in the data sheet are the specifications of the device you have in hand. Now figure it. I mean, if you're buying a device and they're made, 10 million of the devices and so on, what the data sheet is going to show you is what is typically expected. But there's an up and down range for it, so that there are variations in the characteristics of the device. Of course, when the device works, it gets warm, so those characteristics change. And then current passing through resistors and other passive components cause them to heat up, and their value change because they're being asked to dissipate energy. Once something is working electronically, it means current has to pass through, and once current passes through any electronic device except a superconductor where the resistance is zero, it will be dissipating heat, and therefore its value is going to change. So what you're trying to do is that you must have some way of stabilizing the gain of the amplifier against the variation in all these things. So when you set the gain of the amplifier, let's say a voltage gain of 100, right? When you're using the amplifier in the lab, which might be 20 degrees C, or you come outside and it's a really hot day in the middle of the day and it's 35 degrees C, or it's like a day like today where it may be 28 degrees, but the humidity is 100%. Under all of these conditions, inside the AC, the lab, the humidity is probably 10%. It's very dry. So you design it in the electronics 2 lab upstairs. You come out on a day like today where the temperature is 8 degrees hotter, but the humidity has gone from 10% to 100%. You want the amplifier to still be giving you something of 100, a gain of 100, maybe plus or minus 5. right? So you don't want it, you will have to kind of see what range is acceptable to you. But you certainly don't want, when you go outside on a coolish, humid day like this, that the gain that was supposed to be 100 is 25. Then that's defeating the whole purpose. The other thing is that amplifiers, remember, it's not only DC, and amplifiers designed to amplify a range of frequencies from DC all the way up to very high. And one of the things you want to do is to maximize the frequency response of the amplifier. Think of your cell phones. We said that already. Radio frequency amplifiers operate in the gigahertz range. So to get that sort of bandwidth, the characteristics of the amplifier have to be in such a way that you get that. And then things like linearity. Remember, linearity has to do with if I put a 1 volt change on the amplifier and get a 10 volt change at the output, right? If the 1 volt changes from 0 to 1 volt and I get a 10 volt change, if the output, the input range now instead of 0 to 1 volt is 5 volts to 6 volts, then I should get the same 10 volt change on the output. Okay, that's what linearity basically means. Distortion, we kind of understand what that means, but basically, if you think about sinusoidal waves, a nice sine wave going in, what you don't want is after the amplifier has gotten through with the signal, that instead of that, what you get is that it's amplified and then it's clipped. So you're getting a nice sine wave and then it's clipped, right? Because the amplifier, the supply for the voltage, for instance, is not high enough to allow the signal to be amplified. This creates a lot of distortion. So what is going in, if it's an audio signal, for instance, you're not going to hear the same thing coming out. And then noise takes a variety of approaches, but sometimes it could be interference. So instead of the signal coming out, where the signal is, it has a lot of, other signals riding on it. And what you really want is somewhere inside of there. So you want to keep that low, you want to keep the distortion low, and you want to keep the linearity as good as possible, right? All of those are what you want in an ideal amplifier. So one of the ways of sort of guaranteeing that with the amplifier is to put something called feedback on the amplifier. And the feedback now takes that amplifier that you would have carefully designed, and you're now going to take some of the output of the amplifier and send it back as a sample. And what that feedback does, especially the feedback is in a form called negative feedback, what it does, it actually helps in all of those characteristics of the amplifier. So it improves the input and output impedances, it improves the gain, makes the gain less dependent on changes in the components of the device, and it also improves in distortion and in the frequency response and so on. This particular type, as we said, is negative feedback. And remember what negative feedback does when we were talking about in controls. Negative feedback, you are subtracting some part of the output from the input. In other words, you're trying to, if the output went in some direction that you didn't want, you take some of that and you subtract it from the input so that you change the input in such a way to bring the output back to where you want it. We also saw, as a revision, that there's a version of this circuit where we take the feedback and we supply it in a positive form. And when we do that, we create these devices called oscillators. Because oscillators are unstable. Remember what an oscillator essentially is that with no input, you get in a signal coming on the output. So that is something deliberately that we do. It is a deliberately unstable amplifier. It's an amplifier that we want it to be going, the output to be going up and down, but in a predictable way. But if you want the amplifier to do the other types of work that we want, which is to take some low signal and amplify it nicely for us, then the feedback has to be negative. And we already know that if I give you a block diagram like this, and this is G and this is H, that the transfer function of this is G over 1, because it's negative feedback, 1 plus GH, right? The closed loop gain. So the closed loop gain, right now we can see that this now, if the open loop gain is G, the closed loop gain is going to be a little bit less than G. All right? So it's reducing the closed loop gain, but is giving us, it's reducing the open loop gain, but it's going to give us some advantages, as we will see. Right? Make sense? If you're following, let me know, and or if it's something that you want me to repeat. Yeah. Right, and we saw this now. So in terms of the input to the amplifiers may be voltages or currents, and so that the feedback may be a voltage or a current, and the feedback network, what do you call it? The summing junction here may be something like a summing amplifier, an op-amp amplifier, for instance, that you set up as a summing amplifier, and so on, right? And the summing, remember, of course, amplifiers, we can have either voltage or current, right? So in terms of the amplifiers now, the two characteristics that we deal with are voltage and current. And because there are two of them, we have 4 possible combinations of these amplifiers that we can deal with. And the classifications are, of course, voltage amplifiers. Those are the ones that you know, and we'll talk about the actual examples. These are the ones that we, almost every time, if you ask anybody what is an amplifier, inherently they will tell you. So you take a small voltage and then you stick and you get a larger one coming out, right? Current amplifiers do the same thing for current. And then there are 2 variations of these, transconductance and transresistance. So let's just review that quickly. Of course, the voltage amplifier, voltage in and voltage out. And the sort of model for the amplifier as a block is that the amplifier has a high input impedance, right? So the input impedance here in is high. It gives you a voltage gain. So the output, we model it as a voltage, an ideal voltage source and an output resistance. So you want this to be as close to 0 as possible so that all of the voltage drops across the load. And you want the input impedance to be high so that all of the input voltage drops across the input impedance here, right? This kind of circuit, of course, because it's a voltage model, a circuit with a voltage in and a voltage source, is a Thevenin equivalent circuit, right? And of course, you know that the V in and V out relationship is through a voltage gain here. The current amplifier is one that takes a current in and gives you a current out. You'll see the kind of examples of that. Once you're dealing with ideal sources, the current in is a current source in parallel with a source impedance. And the amplifier itself, of course, has its input impedance. And because it's a current amplifier, it has a current gain, AI, and it has a current, an output impedance that is in parallel with the current source. Okay, so in this case, what you want the input impedance very low. So for the current amplifier, you want the input impedance low because you want the current to be going in this way instead of through the source. And then the output impedance you want high so that the current goes this way instead of dissipating itself in the output impedance of the amplifier. And the amplifier has a gain of AI. And then the other 2, and we'll see where you use these because they occur quite frequently is the transconductance amplifier, which takes a voltage in and gives you a current out. Right, so a voltage in and a current out. So you, and I'll talk about the example in a while. So this one now, the input part we model as a Thevenin equivalent circuit, which is a voltage and a series, series resistance. And the output we model as a Norton, which is a current source, an ideal current source, and a shunt resistance. In this kind of thing, a transconductance, because it's taking voltage in, the input impedance has to be high, so all of the voltage drops across here. And because it's a current, a device that is giving current out, the output impedance also has to be high, so it drops the current across the loop. And the relationship between the input and output is something called the transconductance. And the usual symbol for it is a capital G. Right? And then the other one, the final one in the four group amplifier, the four amplifiers in the group, is the trans resistance amplifier that takes a current input and gives you a voltage output. So this one, we take a Norton input because it's a current source. So you want the input impedance here to be very low, so that whatever the source is supplying, the current goes right into the amplifier. And then the amplifier is producing current coming out, but the current, it's producing voltage coming out, so that what you want is that the output impedance here has to be low, so the voltage drops across the loop. Right? And the characteristics of that is something called the trans resistance, which is they normally use the symbol capital R for it. Okay? So those are the four amplifiers, and they're summarized inside of this table here. The voltage amplifier, the current, the transconductance, and the trans resistance, and the various ideal characteristics that we want. Right? So this is one of those things that I told you. You should be able to reason it out, but it's the sort of thing that I could give you and ask you, okay, fill in this table for me. Right? You have the voltage, current, the input resistance, output resistance to fill in that sort of table, right? And this is good revision too. So when you're revising, practice doing that. And these were some circuit examples. So we will get to that in a little while. Right. So, okay, so the voltage amplifier, I'll just run it through here. The voltage amplifier, of course, the normal thing, this is a common emitter amplifier here, voltage in, voltage out, a non-inverting amplifier, or even an inverting amplifier, it doesn't matter, right? The typical op-amp amplifier circuits are all voltage amplifiers, all right? A current amplifier, a good example of that was something that we did last week. We just did it here. The pass transistor part of the power supply circuit. That pass transistor is taking a base current and is amplifying the base current by the HFE of the amplifier. So the IC is HFE times IB. IC, of course, is the output current for the power supply is typically here, but we always use the assumption for most transistors that IC is approximately equal to IE. So that the useful current coming out of the device is approximately HFE times whatever IB is. And we went through a whole bunch. We have a number of ways of getting IB, including using another transistor here, or using an op-amp, right? Or using a Darlington pair, which basically gives you a HFE by HFE1 by HFE2 kind of thing. But the power supply, the pass transistor circuit in the power supply is an example of a current amplifier. The transconductance amplifier, the transconductance and the transresistance amplifier are devices that I use a lot in in control signaling. When you go outside, when you do your controls, and if you end up working in the controls field in almost any industry, you're going to come across something called current signaling. What happens is that if you think about it, this is one version of it. But if you think about it, a typical control plant is something that is spread over a fairly large area. When things happen in one part of the area, there has to be a way of communicating what is going on in that area to another part of the plant, or to the control unit or the control room and so on. One way of sending the signals is using something called a current loop. So you send something, and what you have is you have some part of the plant, and then you have the control room, and you have a current loop. Essentially, it's DC current going back and forth, and the current carries a low of 4 milliamps to a high of 20 milliamps. Now you can use this. Why it doesn't go to, well, just thinking about it, why wouldn't we go from, if I'm using this just, so something is happening in the plant outside here, okay? Something is happening here, and I want to know what is going on in this point here. So I'm sending a current signal to tell me that. Why wouldn't I use 0 to 20 milliamps, for instance, right? Remember, these are supposed to indicate levels. So you could like a small change to a big change. They use it for a variety of things. They're modulated, and there's a whole standard that governs it. But why wouldn't they go to, why wouldn't they use 0 instead of starting at some odd number like 4? Any idea? Just think like an engineer, think like a designer. Any suggestions? All right. One reason is that if you're using 0, let's say just for argument, we do using digital signaling. So 4 milliamps is logic 0, 20 milliamps is logic 1. If I were to use 0 milliamps as logic 0 and 20 milliamps as logic 1, then there's nothing to let me distinguish a 0 as in a logic 0 from a broken wire. If the wire is damaged, I also will get 0 milliamps being detected in the control room, right? Or if the wire is short circuit and the current is going to ground, then the control room on the other side of the short will be seeing nothing. In that case, you can't distinguish a valid signal from a short circuit or open circuit. So to avoid that, they set the lower limit, and this is a standard that is set internationally. They set the lower limit as 4 and the higher one as 20. Historically, there are some other reasons why the range came in, but the lower range came in so that if instead of 4 you're getting 0, you know there's something wrong with the wire, right? So it's like a self-testing wire. You're supposed to have a minimum of 4 if there's 0 and a maximum of 20. If you're getting outside of those ranges, it's telling you something else is happening around the place. Go and check the wiring, right? So what will happen now is that you need, in most plants and in most control situations, what you're sensing is voltage. But to send a current down the road to signal the voltage, you need a device that will convert voltage to current. And that's where the transconductance amplifier comes in. And there are op-amps that are designed to do that. This particular device is something called an operational transconductance amplifier. So it's an op-amp that is configured to work as a transconductance amplifier. All right? And so you put in voltage in and you get in current coming out. Of course, when you reach on the other side now, you have to have a way of converting the current back into a voltage. So this is where the trans resistance, or in some literature you would see that as also called a trans impedance, but a trans resistance amplifier. So this one takes a voltage, a current in and gives you back your voltage coming out. All right, so if you are sensing a voltage, you convert the voltage to a current, send it down the road, right? And then at the end of the day, when it's arrived at the destination where you want to make use of it, now you have to convert it back to the voltage again. Okay, so again, you're going to meet it. And then here's another type of independent sort of application: photosensors. Photodetectors typically create current in response to light. So like a photodiode, the output of the photodiode is a current flow instead of a voltage. So the brighter the light comes on the diode, the more current that will flow through it. So you need a way of amplifying the current, and that's where the transresistance amplifier comes in. And I had a question here from way back when we did it in class. What is the simplest current to voltage converter that you all have encountered already? Anybody remember that? What's the answer to that question? What is a simplest current to voltage converter? Anyone? Something that can pass current through and get a voltage out. How about this? You pass current through a resistor and you get a voltage across the resistance, right? Totally passive and very predictable. That's the simplest current to voltage converter that there is. All right? So you don't have to do anything. If you want to sense a current, pass it through a voltage. Pass it through a resistor and measure the voltage across. All right? Right. So in terms of feedback topologies now, we have the types of amplifiers. There are 4 types of amplifiers. And the amplifiers now, depending on how we do the feedback, and we covered this a little bit in the December exam review. There are 4 combinations now, depending on what you how you do the feedback. There are 2 things, only 2 things that have, you have voltage input and you have current input. You have voltage output, V in, current in, voltage output, and current output, right? So if you're taking voltage, look at the name here, right? So the first thing tells you what it is you are sensing, and the other way is telling you how you're feeding it back. So a voltage amplifier, which is voltage in and voltage out, voltage amplifier, voltage in, voltage out. So there's a voltage amplifier here. It means that what I have to sense, what I have to feedback is voltage. And if I'm sensing voltage, how I feed the voltage back has to add or subtract to the input. If it's negative feedback, the voltage has to subtract from the input. So I have to feed the voltage back in series with the input, right? So a voltage amplifier senses the voltage. So in terms of the name here, what you have here is what you are sensing and how it is fed back. So the voltage amplifier is sensing voltage and feeding it back in series. What does the transresistance amplifier do? Remember the transresistance? The transresistance amplifier is current in and voltage out. So it's current in and voltage out. So if the input current, if the input here, let me get another color here, the transresistance amplifier is current in and voltage out. So what am I sensing? If I have to feed it back, the output is what I sense. So I have to sense voltage, but I have to feed back current. If I'm feeding back current, to the feedback for current has to be in parallel with the current that is in, so that the feedback now has to be shunt, right? The transconductance amplifier is current in and, sorry, it's voltage in and current out. The transconductance amplifier, another color here, what other color? Let's do this one. The transconductance amplifier is voltage in and current out. So if it's voltage in and current out, right, what am I sensing? I have to sense current to feedback, but my feedback has to be a voltage because it's input voltage, so it has to be series. And then the last one, the current amplifier, is current in, what color do we have here? The current amplifier, sorry, is current in, let me just draw this better here, where's my pen? Current in and current out. So what am I sensing? Current. And if I have to feedback current, it has to be in parallel with what went in. So it has to be in shunt, right? So the first term tells you what you are sensing, and the second term tells you how you're feeding it back. And here are the configurations to show what we mean. So the voltage series, which is a voltage amplifier, you're sensing the voltage. So the voltage, if you're sensing voltage, how do I sense voltage? I sense the voltage across the load. So I have to put the feedback. This is my load voltage here. So I have to sense the voltage across here. And I have to feedback the voltage. Now it's negative feedback, so that the voltage has to go this way. Right? Notice the arrow and the sign. So the feedback voltage is going this way. So that it subtracts. So that V in is Vs minus the feedback voltage. Right? Yeah, no, maybe. Make sure you're following what I'm doing, okay?
Yeah.
The transresistance, we are sensing voltage on the transresistance, meaning that we have to measure voltage on the output. But the transresistance has to feed back current. So if it is feeding back current, the current has to go in parallel with the source current. So look what is happening here. So the source current now, because this is subtracting, so once the source current is here, the feedback current has to go here so that it reduces the input I in. So this is a negative feedback here. It's subtracting from the input current, I in minus IF. Right, that's a negative feedback here. The transconductance, we have to sense current. So the only way to sense current is to put it in parallel with the, or in shunt with the output. In other words, you have to make sure that you break the line, you're not going across the load here. So you put it here in, in series with the load, right? So the current is flowing this way. So the output current goes into into your amplifier, into the feedback network. Because it's a transconductance, it's taking current, but we have to send voltage back. And again, we have to send it negative. So the voltage has to go back this way. That's the negative feedback. And the last one is the current amplifier. So the current, to get the current coming through, you have to break the circuit and put your output, right, in series with the load. But the feedback here has to be in shunt with the current source, your signal. So this is the I feedback here, so that again the input current is reduced by the amount of IF, right? IS is equal to these two, so this is subtracting from IS to give you a little bit to reduce. That's the negative feedback right there. All right. And of course, we know the feedback calculation here. Once you do that, we mentioned this before, that we for the electronics circuit or electronics analysis, normally in signals we call this G and H. In electronics, the terminology used is what we call A for the amplifier gain, and the feedback network gain is beta. All right, so that the loop gain here is G over 1 plus GH, which is A over 1 plus A beta. The loop gain, okay, because it's negative feedback, the sign is positive. All right, the sign is positive here. If it was positive feedback, like when we were creating the oscillators, you get A over 1 minus A beta. And what we were trying to do is to make this close to 1. So the thing oscillates, right? And this was just like how you express it in decibels, which we've done a little bit. So some conditions that must be satisfied is that first, the signal, the output signal, the input signal must only go through the amplifier and not through the feedback network, right? So once I put my signal into here, this input signal here must only go through the amplifier. I don't want anything going through here, right? And then the feedback signal is transmitted from output to input through the beta block and not through the amplifier, right? So the feedback has to, the feedback must go this way, right? And not this way, right? And then the reverse transmission factor, or the gain of the feedback networks, is independent of the load and source resistances. Okay, we can't have this happening at all, because once you don't know what the amplifier is going to do, it is designed to supply. It is designed to supply a particular load, and the source, of course, is wherever you're getting the voltage or current from, right? This cannot depend on the load resistance, because it will mean every time you change the load resistance, the feedback gain will change on you, and that's going to create all sorts of difficulties. All right. So stop that. So everybody clear? Or are there any questions on first of the types of configurations that we have, and how the configurations work, right? You have 4 possible combinations. There are only 2 things you can amplify, which is voltage and current. But you can also supply voltage and current. So if you have so the combination of those two sets of things, what you could sense and what you could supply, creates 4 combinations of amplifiers. And then the feedback, likewise, depending on the amplifier, you have to be able to sense a voltage and feedback a voltage, sense a voltage and feedback a current, sense a current and feedback a voltage, or sense a current and feedback a current. Okay? So all of those and how to draw the circuit. So you, let me just share this again. All right, you are expected to know, where am I there? Just let me get back to that slide again. There's feedback amplifier 1. Sure, all of a sudden, I do. Right? So I expect you to be able to, just go back here. These 4 configurations here, the voltage series feedback, the voltage shunt feedback, and the amplifier associated with it, the current series feedback and the amplifier associated with it, and the current shunt feedback and the amplifier associated with it. Notice at no point in time have we discussed any actual circuit. So you're not asking, I'm not asking you to draw any transistor or op-amp circuit to do this. That was not part of what I wanted to do for the course. I wanted people to understand what the various types of feedback mean. Once you do that, then we could start to look at amplifiers or analyze amplifier designs and the like. All right. So you have to understand these types of configuration. So everybody all right with that? Anything not clear or that you still want clarified?
So far, okay.
Right. So far, okay. Of course, when you start to review it is when some other things start coming up, which is fine, right? When you review it or you're reading this stuff, all of a sudden there are things that you suddenly say, well, wait a minute, that aren't making sense, right? Anything that isn't making sense or this doesn't conceptually sound correct, you have to let me know as soon as possible, okay? Right. So these were just some circuit things. Forget that for the time being. And what this part of the lecture did was to show now for the various types of amplifiers, which is kind of leading to the exam question, what are some of the things that feedback does? Remember, we made the case that for voltage input amplifiers, that we want the input impedance to be as high as possible, right? So for voltage amplifiers, we wanted the input impedance to be high. For current input amplifiers, we wanted the input impedance to be low. And then the other way around, for voltage amplifiers, we wanted the output impedance to be low. And for current amplifiers, we wanted the output impedance to be high. All right, because you're looking to, it depends on where you want to drop the signal. And then we want to stabilize again, and then we want to improve the frequency response. So the next series of slides dealt with how the particular topic was resolved. So if we're looking at input resistance, which is what we'll just quickly look at today, the crux of it here is that if the feedback, remember the input impedance is there, we could draw, let me see if I have, right. So this is a device with voltage series feedback. If it is voltage series feedback, it means that I'm sensing voltage and feeding it back in series with the input. So this is my voltage amplifier here. Right? So if I'm sensing voltage and feeding it back, notice the polarity here because it's negative feedback, so it's going to subtract from the input voltage. So the calculation here, therefore, is that if I have a source voltage, right? If the feedback is applied series, then since the voltage is opposing the input voltage, right? And see what happened here. So that this voltage here now, Vn is Vs minus Vf. All right. So because of that, if I supply Vs, the feedback is reducing the amount of input voltage that is appearing across here. All right. So that is the equivalent of saying that if the input voltage is reduced, that the input impedance has increased. Okay, so the input, by opposing it, I'm taking less current coming in, so it looks like the input impedance has gone up. All right, because I'm bucking, if Vn is reduced, then Vn over In, sorry, let me put it the other way. If Vn is reduced and this is unchanged, it means that In is reduced. In reduced means that the input impedance going in inside of here has been increased, because the only way you could reduce current is by increasing the resistance of the current. All right, and this is the sort of calculation inside of here. So the feedback voltage series feedback has the effect. Where are we? Once the feedback voltage is applied in series with the input, then because the voltage opposes the input signal voltage, the current is reduced from what it would have been without the feedback. So the effect is an increase in the input resistance. As far as the source is concerned, if I can't get as much current into, just think of me, if I'm a current, so if I'm something supplying current to a device, then if the amount of current I could supply to the device is being limited, it means that I am seeing a high resistance going into the device. Yeah. So for if the voltage applied is, if this feedback supplied is voltage, then we see an input in impedance. If the feedback is current, then the reverse applies. Right? Let me just, we have the calculation here. Right? So if the feedback is current, then notice the current feedback, and again, we're drawing this schematically. You can go back to the circuit where we have the amplifier and the feedback. So you have A and you have beta, right? Voltage shunt feedback means that the amplifier, if I'm measuring voltage, it means voltage is what being fed back. So this is what I'm measuring here. So I have a voltage feedback. If it is current or shunt feedback, it means that I'm feeding back current into the circuit. So the particular amplifier is a trans-resistance amplifier. So the trans-resistance amplifier is a current source supplying the input impedance here. If I have to feed back current, negative feedback in here, it means that the feedback current has to go in parallel with the what do you call it, with the source current here. So I have to send the current back in such a way that the current is basically opposing. This is current now, not voltage. This is I, this is IF, is opposing the current that the source is sending, right? And you do that. The model for this, of course, is to put the current source in parallel with the signal source. All right. So you have to remember all of these configurations here. How you do the current configuration, and then we have the derivations going on. Okay. So I will get to that. Yeah, this is I'm talking about current here, remember? This is current here. I just drew it like this, but this is current. This is a current signal that I'm opposing inside of here. Actually, should I drew it the other way around? Yeah? Should the current would be in this way, right? So current is going to be across here, right? Let me just erase a little bit here. Hold on. Draw this back properly here. The current, I'm putting it back in such a way that the current here is subtracting from the the source current itself. So this is the IS, and this is IF going down here, IF, and this is I. Okay. And we have the calculations for it, which are fairly straightforward inside of here, right? And we'll review that. I'll start back there on Wednesday. Okay, so questions?
So there's a reason why you're using two voltage source, two current source.
Right. So yeah, for generally or in this particular application here.
In this application.
Right. Okay. So the shunt feedback is current, right? Every time you see this, this is shunt, also known as current, right? So ideal current, first off, this only works, the voltage shunt feedback is for the transresistance amplifier. Transresistance amplifiers is current in and voltage out, I in and V out. The model for this, if you forget the feedback for the time being, the model for the input is a current source, and of course it has a source resistance, and it's going into the amplifier here, right? So this is my current source, and this is my amplifier input here. Without anything, this current is going straight into the amplifier. The feedback is now current feedback. So to model this, ideally, what I want is, because it's feedback and it's negative feedback, I have to have something that is subtracting current from that. Remember, this is the input current here. The feedback current has to subtract from the source current here. This is IS. All right. So I can either draw it like what I did here and send that back to the network. So the feedback is coming via the network, or I could get rid of the network, so I don't have to draw that, and then just put the network as supplying a feedback current. Oh dear. Okay. Just draw back the lines here quickly. Right. So let's do it here. The feedback, what I could do, I can model the feedback now as a current source coming this way. Right? And it's subtracting the same way. So I've basically changed all of this. Just model all of that as just a simple, that the feedback network is supplying a feedback current to me. All right? Any clearer?
Yeah.
Mm-hmm. All right. Any other questions? It's a little
Not at this point.
okay, right? It's a little odd because what we've done here is to go from this diagram to this diagram. This is a little bit neater because you don't have to remember where to put the lines. You're sensing voltage, you're feeding back current, or you're sensing voltage and feeding back voltage on the line. This one, if you're feeding back voltage, then it's a voltage source. If you're feeding back current, then it's a current source. If you're amplifying voltage, then the input is a voltage source. If you're amplifying current, then the input is a current source. Okay? Fair enough?
Yeah.
All right. So we almost there in terms of answering the questions. Yes, Samira, what's the question? Let me see. The grades. Right, okay. Normally, right, so normally the answer is no. But right, we having, because a number of people are repeating courses, if you all do very well on your summer courses, because some of you all are doing 2, some of you all maybe even doing 3 courses this summer. If you all are doing very well, at the end, if you have a good mark, we will try to make a case to see if we can have the RTW rescinded. But I can't say anything at this point in time. It's just something that we will try so that it doesn't, to try to avoid people having to stay out for the because of the RTW. But part 1 of it is that you all have to do well. So if you get really good marks in the summer courses, first off, you apply to have that credited back to your record, because remember, summer semesters are separate thing. It's not counting to your time in the system. It's a private arrangement where you're paying the university to do over the courses itself. So part 1 is to pass very, very good. So if you all get good marks, right, then we will be in a position now to make a case for you going forward that, okay, student this and the other did very good. So because of that, they have basically, passed all the subjects that they would have been repeating the next come September or whenever. So let's let them go forward, and we'll have to make an application for that later on. That will be after somewhere between July and August kind of thing, to try and get that kind of thing done. But first step is for you all to pass, all right, and pass well. Okay. Okay, guys. So any other question? All right. So let me stop the recording.